Suppose you lived in the time of Isaac Newton or Galileo Galilei or Tycho Brahe or one of those other very famous scientists from before the modern era. And you notice that when you drop an object, that object accelerates towards the surface of the Earth. And then you conduct an experiment by dropping many different types of objects, and you realize that as long as you can neglect air resistance, all objects that you drop accelerate towards the surface of the Earth at the same rate. And so you want to measure what is this rate of acceleration of objects that are moving under the influence of gravity. So would you be able to set up an experiment where you could easily measure the acceleration due to Earth's gravity? And I want to emphasize the word easily here. The first thing you might think of is if you are trying to measure the acceleration due to Earth's gravity, you take an object, you could possibly mark out meter-long segments along the side of a building, you drop the object, and you see the object is falling somewhat slowly at first, but it quickly picks up speed as it accelerates downward. But what would you do? You would eyeball where is the object by that building, but then for timing, remember, we are talking about science being done before the modern era, before we had access to lasers and quartz clocks and data studio software. So for measuring time, we would just need to be counting in our head, 1,000, 2, 1,000, and so on. So this would be a very challenging measurement to make. One way around measuring the acceleration due to gravity was to use Atwood's machine. Atwood's machine is a very simple machine. It consists of two masses. Presumably, we know what these masses are. One mass I'll call big M, and the other mass I'll call little m. And these two masses are connected by a rope, and that rope is slung over a pulley. So right now, we are assuming we have two masses, of which we know their masses. We went into our lab, we picked up the masses ourselves, and then we're going to assume big M is the larger of the two masses. And this pulley that we attach the rope that connects the masses to, the pulley is very free to move. So the pulley offers practically no resistance to the motion of the masses. And the rope itself we will assume to be massless. Now, a real world rope will never be massless, but to a very good approximation, we'll assume the rope to be massless. So only big M and little m are the two relevant masses in this problem. Now, if we want to measure the acceleration of an object, and we are limited by the technology available to us, it would be best if that object is moving slowly. Because if I have to count in seconds in my head, that's going to introduce a lot of error. But if an object is moving slowly but accelerating, it will be easier for me to more or less figure out at what rate that object is accelerating compared to something moving very rapidly. So how will Atwood's machine actually help us measure the acceleration due to gravity? Well, presumably what we're going to do is we're going to measure an acceleration by watching these masses move just by eyeballing them, counting time in our head. And if we watch these objects accelerate, we'll be able to say the acceleration of the objects is equal to some stuff based on known quantities. Presumably big M and little m will be important here. And somewhere in here, there will be the acceleration due to gravity. Now today, we know that the acceleration due to gravity is 9.8 meter per second squared. But at this time, hundreds of years ago, we didn't have physics textbooks that gave this number to us, and this was a very difficult to measure quantity. So how do we go about measuring the acceleration due to Earth's gravity? The first thing we're going to do is we're going to apply Newton's laws to Atwood's machine. So the way I have Atwood's machine set up right now, I place the large mass up higher than the small mass, and I'm presumably holding this large mass up. But if I let go, you know that gravity will pull both of these masses downward, but because the larger mass is over here, the large mass will end up descending, and the small mass will ascend because the small mass is being pulled up by the larger mass. So the first thing I'm going to do when I apply Newton's laws is draw in the acceleration of both of these masses. The large mass will accelerate downward with an acceleration I will call A, and the small mass will accelerate upward with that exact same acceleration. So this mass will accelerate upward with an acceleration A. So we said that both of these masses are going to accelerate at the same rate. One of them is accelerating downward, the other is accelerating upward. We want to be thorough with our positive negative signs. I will choose, as usual, that up is the positive direction. So I will say the small mass accelerates with an acceleration positive A because it's accelerating upward. The large mass accelerates downward with that same amount of acceleration, but because it's accelerating downward, its acceleration is going to be negative A. Now, what's the justification for the claim that the amount of acceleration is the same? Well, to answer that, let's think about what's happening in this problem. Both of the masses are connected by a rope, and we are assuming an ideal rope. So the rope is not stretchy at all. The length of the rope is going to be constant throughout this experiment. As a result of that, if this large mass moves down 20 centimeters, this small mass must move up by 20 centimeters. And if this large mass is descending at a rate of 4 centimeters per second, this small mass must be ascending, moving upward at that same rate of 4 centimeters per second. The positions of these masses, the velocities of these masses, and as a consequence, the accelerations of these masses are coupled together. Whatever is happening to one of the masses, there must be something similar happening to the other mass, because the total length of this rope is going to be constant throughout this problem. So at whatever rate this small mass is accelerating upward, this large mass must be accelerating downward at the same rate. What I'm going to do next is we're going to look at the forces on each of these masses. So I look at just this large mass first, and I could say, okay, what are the forces on it? Well, we know there is the force of gravity on the large mass, and the force of gravity is always pulling down towards the surface of the Earth. So I could draw that in. Here is the force of gravity on the large mass. So I'll say force of gravity on big M. And then I ask what other forces might be acting on that large mass. And I say, well, there is a rope, and ropes pull, they cannot push. So there must be an upward force of tension acting on the large mass. So I'm going to draw that in as well. So I'm going to say here is an upward force, F tension on the large mass. I think about this problem. Are there any other forces on the large mass? Well, there's no such thing as friction in this problem. There's no normal force. There's no air resistance in this problem. So we have successfully accounted for all the forces on the large mass. Now I'm going to ask the exact same question of the small mass. So the small mass, there is a downward pull of gravity on the small mass. So I'll draw this in blue, F gravity on the small mass. There is, just like before, an upward force of tension on the small mass. So I'll draw that over here. So here is the force of tension on the small mass. And just like before, I think about this problem. There aren't any other forces on the small mass, so I have successfully drawn them all in. Now we're going to apply Newton's second law, F net equals ma, to both the large mass and the small mass, and we'll see what we get. So for the large mass, we have, for the large mass, okay, F net equals big M times A for the large mass. I'm going to draw these as vectors. And now what I'm going to do is I'm going to write in the terms for F net, write in the terms for acceleration and the large mass, and I'm going to be very careful about including direction. So I look at this problem, the tension force is upward, so the tension force will be positive. The gravity force will be downward, so that will be something negative. So for F net on the large mass, I have an upward force of tension, so that will be plus F tension minus the force of gravity on the large mass, so minus big M times G. M times G is the force of gravity. And then I set that equal to the mass of the object we are talking about. The acceleration here we said is downward, and therefore my acceleration, when I account for sign, positive, negative sign, because I'm dealing with a vector, I get negative A. So at this point, I have Newton's second law written out for the large mass. Now, if I want to, I could do the exact same thing for the small mass. For the small mass, okay, I have the tension force and the force of gravity will look very similar to what we had before. The only difference is that instead of talking about big M, since we were talking about the force of gravity on the large mass, I now have little m because I'm talking about the force of gravity on the small mass. So I could say tension is up, I get plus F tension minus little mg for the small mass, and equal to, now in this case we are talking about a small mass, so that would be times little m times positive A. All I did here was I applied Newton's second law to the small mass. F net equals the mass of the object I'm talking about times acceleration. F net, I again have tension in mg. Because I'm talking about the small mass and the acceleration of the small mass, the m on the right-hand side of Newton's second law is little m for the small mass. Up here, the m for Newton's second law, we were talking about the big mass, will be capital M. Now, at this point, what I can do is I can think about this problem, and I realize when we talked about tension, the tension in a rope, we said, is the same at every location in the rope. So whatever the tension force is over here, the tension force acting on the large mass will be the same as the tension force acting on the small mass, due to the principle of tension is the same everywhere along the rope. So F tension in both of these equations will be the same value. Now what I'm going to do is I'm just going to compare them. So let's see. I could rearrange this equation to say F tension is equal to, I'm going to bring this mg to the other side. So I get big M times G minus big M times A. And I'm going to do the same thing over here. So I could say the force of tension is equal to little m times G plus little m times A. Now, we said that the force of tension is the same for both masses because it's the tension in a rope. So what that means is this term must be the same as this term. And so I could set these two terms equal to each other. So I could say the force of tension, written from here, if I say F tension equals F tension, from the big mass, I have big mg minus big ma. And from the small mass, I have little mg plus little ma. Now what I'm going to do is I'm going to solve for the acceleration of the masses. It doesn't matter which mass I'm thinking about because we said the acceleration is the same for both of these masses. So I'm going to bring ma to the right-hand side and mg to the left-hand side. So I get big mg minus little mg equals big ma plus little ma. Now what I'm going to do is I'm going to factor out the g on the left side, factor out the a on the right side. So I get big M minus little m times g equals big M plus little m times a. And I'm going to isolate A all by itself. So I could write this as big M minus little m times g divided by big M plus little m. Set that equal to the acceleration. And at this point, I am basically done with what I'm trying to do. I'm just going to write this in a bit neater of a form. And I'm going to write that as the acceleration of the masses is equal to g, which is the acceleration due to gravity, times big M minus little m over big M plus little m. So this is the result I got from Atwood's machine. Now, let's draw another picture of Atwood's machine and let's see what we're trying to do. Think about what we were doing in this problem in the first place. So here was Atwood's machine. I had my pulley. I had my big mass that is accelerating downward. And I have my little mass that is accelerating upward. So I have my acceleration of the big mass, which is down, and my acceleration of the little mass, which is up. So how does this help us find the acceleration due to gravity? So here's the acceleration due to gravity. This is the fundamental term. If we know the acceleration due to gravity, and in principle, if we know the size of the Earth, which we did in chapter 1 example problem, we could use this information to find the mass of the Earth and learn something about the planet that we live on anyway. So how does this result help us find g? Well, remember before that we said we want to be able to measure the acceleration due to gravity easily. So what does it mean for something to be easy to measure? If we're limited by technology, if we are restricted to watching something move and counting seconds in our head, it's probably going to be better if that thing is moving slow rather than fast. And even if something's accelerating, if it's moving very slow and then it's moving slow and then it's moving slightly less slow, that's still going to be much easier to work with than if the object is moving really, really fast. So how is this going to help? I noticed that if big M and little m are very close together, but big M is just slightly bigger than little m, so if big M is larger than little m, only by a bit, then I notice that big M minus little m is going to be a really small number. And if big M minus little m is a really small number, then the acceleration that I observe in this experiment will be very small, and that will make it easier for me to see. In the limit where little m becomes 0, then the acceleration is just going to be due to the acceleration due to gravity, and that won't really help us. So we want big M to be approximately equal to little m, but not quite the same. And that kind of matches what our intuition tells us should happen. If this mass is bigger, but only by a little bit, then this mass will accelerate downward, and this mass will accelerate upward, but this mass isn't going to accelerate upward very much. If they both have the same mass, they should both just stay here forever. Neither one should be able to be pulled downward by gravity because they're both being pulled down by the same amount. If this mass is slightly bigger, then this mass will accelerate downward, but not very much. And if this mass down here goes to 0, then this big mass should accelerate downward at the usual acceleration due to gravity. So we have found that if here we have a term that is very easy to measure because we set up this experiment where the acceleration is very small, we are measuring this acceleration in our experiment. So A is measured. All the terms in the parentheses are known because we go to our physics lab and we take masses of known mass. then we have a fairly easy equation that we could just go ahead and solve for the acceleration due to gravity.